Okay, so far we saw breadth-first search, and that's a way to that's one way to traverse the vertices in a graph and identify the level numbers of the vertices. So if you look at the level numbers, they basically indicate the distance from the starting vertex. So with the level numbers, you can also say what is the shortest path from the starting vertex to every other vertex. So if you start from 1 in this graph, so the shortest path, say from 1 to 6, is going to be 1, 2, 4, 6, and so on. So that's also an application of breadth-first search that we just saw. So to identify the shortest path from the starting vertex to every other vertex, or to decide whether the graph is connected or not, or also to decide whether the graph is bipartite or not. So these are some of the applications of breadth-first search. Now we're going to look at one more algorithm, and we'll see this also in detail, called DepthFirst Search. And this will follow a different way of traversing the vertices in the graph, different from breadth-first search. So let us see how we do this. Now, for breadth-first search, we used a queue to keep track of the vertices we visited. Now, for depth-first search, we'll use a stack to keep track of the vertices we visited. So that is a major difference. Okay, so again, we can start depth-first search from any vertex in a given graph. As a convention, we'll start with a lower ID. Or if the vertices are alphabet ID, so you can start with the lower alphabet. Alright, so start with vertex 1. So we so it's a stack, so you should say we push vertex 1 to the stack. Now instead of level numbers, here we keep track of what is called the push order and pop order of the vertices. That means what order we push the vertices in the stack, and in what order we pop the vertices out of the stack. So now vertex 1 is the first vertex to be pushed into the stack. So we say its push order is 1. So you always indicate, as we go through the algorithm, we're going to eventually come up with what are called the push and pop orders of the vertices. So for each vertex, we're going to have a push order and a pop order. So it's a tuple. So the first number indicates the push order, the second number for that vertex indicates the pop order. So eventually for each vertex, we are going to come up with a push order and pop order of those vertices as we do the depth-first search. And we can make use of that push order and pop order later for some applications. So let us go through this example to see first how to do depth-first search. So we push vertex 1 to the stack, so that's the first vertex to be pushed. So we say its push order is 1. We have yet decide the pop order, so we leave it as it is. So we push vertex 1 to the stack, that's initialization. So now we go through the iterations. So what we do in each iteration is we kind of do what is called peek. We don't pop from the stack, we do a peek operation on the stack. So you know what is a peek operation means. You just look what is in the top of the stack. So when you look in the top, what is in the top of the stack, it is vertex 1. So now you visit one of the neighbors of that vertex that is in the top of the stack. So 1 is in the top of the stack, so you visit one of its neighbors that has been not yet visited. So for vertex 1, you have 2, 3, and 7 as the neighbors. So to break the tie, you will decide to visit vertex 2. Now again, you could visit any of the neighbors of that vertex. So just as a convention, we will visit the lower ID neighbor first. That is not been yet visited. So vertex 2 has not been yet visited. So we will visit that vertex. So when you visit a vertex for the first time, we will call that edge to visit that vertex as a tree edge. And we also push that vertex that we just visited to the stack. So 1 is still in the stack, and we push 2 to the stack. So the top of the stack currently has vertex 2. Now we also set the push order for vertex 2. Vertex 2 is the second vertex to be pushed to the stack. So we say its push order is 2. So that's the iteration. So just look into what is the top of the stack and visit an unvisited neighbor of that vertex. So you go to vertex 2 in this case and push it to the stack, as well as set its push order to the next push order number. So far we pushed one vertex to the stack, so push now the second vertex to the stack. So now continue the iterations. So in the next iteration, again look into what is in the top of the stack. So the top of the stack has vertex 2. So now visit one of the unvisited neighbors of vertex 2. So vertex 2 has 4 and 7 yet to be visited. So we can visit 4. So again now mark that 4 has been visited. So you push vertex 4 to the stack and set its push order to one more than what is the last push order. So we've so far pushed 2 vertices. So vertex 4 is the third vertex we push to the stack. And we mark that edge to 4 as a tree edge because that edge was used to visit vertex 4 for the first time. So mark that edge as a tree edge. So now vertex 4 is in the top of the stack. Visit one of the unvisited neighbors of vertex 4. So for vertex 4 you have 3, 5 and 6 that have not been yet visited. So you pick one of them. So we break the tie by picking the lower ID neighbor. So we pick vertex 3 and push it to the stack. So we set its push order to be 4 because that's the fourth vertex now to be pushed to the stack. And mark that edge between 4 and 3 as a tree edge. Now you can kind of feel by now that this is called depth-first search because you're just going as deep as possible. So started with vertex 1, then visited vertex 2, one of its neighbors, and just keep going further down. So from 2 we went to 4 and keep going as long as we can. So now we are where we just went from 4 to 3. So you could guess by now the next iteration will be now look at the top of the stack and visit one of the next visited neighbors of vertex 3. Now if you look at vertex 3, now there's a new case to be we have to deal with. So we have two neighbors of vertex 3, right? So that are not yet for which the edges have been not yet classified. So 4 is also a neighbor of vertex 3, but 4 is a neighbor that has been already visited, and that edge to 4 has been already classified as a tree edge. Now 1 is a vertex that has been visited, but that edge has not been yet classified between 3 and 1. Now 5 is a neighbor that is not yet visited, so of course we would not have classified that edge yet. So let us finish off this neighbor 1 that has been already visited. So all we have to do is, since 1 has been already visited, which means it is already in the stack, it's pushed into the stack, but that edge to 1 has not yet been classified. So if you have an edge to the vertex that is still in the stack, okay, that also means this is an undirected graph. So later we'll see different cases for directed graphs. So for undirected graph for now, if you have a vertex that is to which that edge has not been classified yet, but that vertex has been already visited, that vertex should be in the stack. So vertex 1 is still in the stack and this edge is not yet classified. So we should call this edge as what is called a back edge. So it's similar to a cross edge, but we use a different terminology for depth-first search. So this edge between 3 and 1 should be called a back edge. So that's all we need to do, just call this edge as a back edge. Now also, as an application of depth-first search, we can use depth-first search to decide whether the graph has a cycle or not. So last class I kind of introduced to you what is meant by cycle in a graph. So a cycle in a graph is what? A sequence of vertices such that you can start from one vertex, go around and come back to a starting vertex. So such a sequence is said to be a cycle. Now we can use depth-first search to decide whether the graph has a cycle or not. So how you decide whether a graph has a cycle in depth-first search? So when you identify a back edge, like this edge 3,1 is a back edge. So the presence of a back edge as you do depth-first search indicates the graph has a cycle. Now what vertices are part of the cycle? That sequence that you visited that is the stack will be the vertices that are part of a cycle. So for example, here you started with 1, went to 2, then went to 4, then went to 3. Now you have a back edge between 3 and 1. So that sequence of vertices that you pushed and you now ended up with this back edge will be the vertices that are part of the cycle. So 1, 2, 4, 3 are the vertices that are part of the cycle. So that's one application of DepthFirst Search. You can use it to identify the vertices that are part of a cycle. Now, that is what we have to do with vertex 1. Call this edge as a back edge. Now, for vertex 5, that edge has been not yet visited, classified, because vertex 5 has not been yet visited. So we push vertex 5 and call this edge as a tree edge. So, and also set the push order of vertex 5 to one more than what we have pushed so far. So far we have pushed 4 vertices. So set the push number order for vertex 5 to be 5 and call this edge as a tree edge. So vertex 5 is now in the top of the stack. So now for vertex 5 you have 2 neighbors for which the edges are not yet classified. So we have to look at those 2 neighbors. So for neighbor vertex 4, it's already pushed the stack. So we should call that edge between 5 and 4 as a back edge, because that edge is to a vertex that has been already visited. It is pushed into the stack. So that is all we have to do for this edge between 5 and 4. Now vertex 6 has not been yet visited. So we push vertex 6 to a stack and set its push order to be 6, because that's now the 6th vertex to be pushed to a stack, and mark this edge to vertex 6 as a tree edge, because that's used to visit the vertex 6 for the first time. So vertex 6 is now in the stack. So now look into the stack, and the top of stack is 6, so explore the neighbors of 6. So the neighbors of 6 are like 5 and 4, but 5 is already visited and the edge is classified. So for 4, which is also already visited, we have to classify this edge as a back edge. So 6, 4 is now a back edge. Now that's all we can do with vertex 6. We looked at its neighbors, classify the edges with the neighbors. So you cannot do anything else. We cannot go visit any other vertex from vertex 6. If you can go further down to another unvisited neighbor, we can add that neighbor, push the neighbor to the stack and move on, but we cannot do that for vertex 6. So when you cannot go further down, that's the time we pop that vertex out of the stack. So when we pop the stack, of course 6 is in the top of the stack, so 6 comes out of the stack. So vertex 6 is the first vertex to be popped out of the stack. So we now start working on the pop order. So vertex 6 is popped out, it's the first vertex to be popped out, so we set its pop number to be 1. So vertex 6 is now out of the stack. So the stack currently is 5, it's 5 at the top. So look into the top of the stack, which is vertex 5. So now explore vertex 5, see if you can go further down to any other unvisited neighbor. If you can go further down to any unvisited neighbor, you would push that neighbor to the stack and move on further down. But we cannot do that for vertex 5 because all the neighbors of vertex 5 already visited. So it's also time to pop out vertex 5. So you pop out vertex 5. So vertex 5 is the second vertex to be popped out of the stack. So when you pop out vertex 5, the top of the stack will be 3. So now look at vertex 3 and see if you can go further down to any unvisited neighbor. So again, we cannot go do that because all the neighbors of 3 have been already visited. So it is time to pop out vertex 3 also. So vertex 3 is the third vertex to be popped out of the stack. So the top of the stack is now vertex 4. Now look at the neighbors of vertex 4. All the neighbors of vertex 4 are already visited, so we cannot go further down from vertex 4. So vertex 4 is now also popped out. That is the fourth vertex to be popped out of the stack. So the stack currently has 2 and 1. So 2 is in the top of the stack. So look at vertex 2. Now there is one unvisited neighbor for vertex 2. So you have to go further down to that neighbor. So you don't pop out vertex 2 because it's not like a dead end yet. We can go further down from vertex 2 to some other unvisited vertex. So push vertex 7 now to the stack. So stack currently has 7 at the top. So far we continue the push order. So far we pushed 6 vertices in the stack. So vertex 7 is going to be the 7th vertex to be pushed into the stack. And then call that edge to between 2 and 7 as a tree edge, because that edge was used to visit vertex 7 for the first time. So it's called a tree edge. So vertex 7 is in the top of the stack. So see if you can go further down from vertex 7. Now 1 is the only neighbor with which the edge has not been classified. 2 is not, the edge is already classified. So it means you cannot push vertex 1 to the stack because it's already pushed to the stack. So the only thing we can do is call this edge as a back edge between 7 and 1. So those are the two neighbors of 7, and no other unvisited neighbors of 7. So it's time to pop out vertex 7 from the stack. So far we popped out 4 vertices from the stack. So we pop out vertex 7 as the 5th vertex from the stack. So that's the pop order number for vertex 7. So the stack again has 2 in the top of the stack. So now we cannot go anywhere else from vertex 2. So now is the time to pop out vertex 2 from the stack. So vertex 2 is the 6th vertex to be now popped out of the stack. And the stack now currently has 1 at the top, and that's the only vertex. So we cannot go anywhere else from vertex 1. So it's time to pop out vertex 1 from the stack. So that is the 7th vertex to be popped out of the stack. Okay, so the stack eventually becomes empty. And by the time the stack becomes empty, we have visited all the vertices. So again, we can use DepthFirst Search to decide whether all the vertices are connected to each other or reachable to each other, means they are the same component. So like we use BreaderFirst Search, you can also use DepthFirst Search to decide that, whether all the vertices are connected or not. So yes, so in this graph, all the vertices are connected, means they are reachable to each other, and they are said to be in the same component. Okay, so this is how you do DepthFirst Search. So the end result of DepthFirst Search are going to be like you're going to classify the edges as tree edge and back edge, and also identify the push order and pop order of the vertices. Of course, the push order and pop order depends on the starting vertex. So if you started from vertex 1, you're going to have vertex 1 as the first vertex to be pushed, and so on. So if you start from some other vertex, you're going to have a different push order and pop order. Okay, so that's something you have to remember. So later we'll see several applications of DepthFirst Search, and as part of that we'll make use of the tree edges, back edges, and push order and pop order. Now let me go through one more example of DepthFirst Search just to make sure everyone got it. So here again you could pick any starting vertex as a conventional pick the vertex, the lower ID as a starting vertex. So we'll call now just one terminology. So if you just put together the tree edges, we can get what is called a DepthFirst Search tree, starting from the root, the starting vertex 1. So just put together all the tree edges, that's called a DepthFirst Search tree. Okay, that's something you can put together with the tree edges. Alright, so start with vertex 1. So push vertex 1 to the stack. So vertex 1 is the first vertex to be pushed into the stack. So go to one of the unvisited neighbors of vertex 1. Now all the neighbors are not yet visited. So go just identify the lower ID neighbor, which is vertex 2, and push vertex 2 to the stack. So vertex 2 is the second vertex to be pushed to the stack, and we call that edge to vertex 2 as a tree edge. Now we are at vertex 2, that's in the top of the stack. So go down further, there's only one neighbor that is not visited for vertex 2, which is 3. So push 3 to the stack, and 3 is the third vertex to be pushed to the stack. Then call that edge between 2 and 3 as a tree edge. Now from 3 you can either go to 4, 5 or 7. We break the tie by going to the lower ID neighbor. So we push vertex 4 to the stack. So vertex 4 is the fourth vertex to be pushed to the stack. We call that edge between 3 and 4 as a tree edge. So the top of the stack currently has vertex 4. Now from vertex 4 we cannot go down further to any new vertex, because the only other neighbor we have for vertex 1 is 1, which is already pushed to the stack. So we should call that edge between 4 and 1 as a back edge, because that one has been already pushed to the stack, visited. So there's nothing else we can do at vertex 4. We cannot go further down to a new vertex. So it's time to pop out vertex 4 from the stack. So vertex 4 is the first vertex to be popped out of the stack. So we pop out vertex 4, that means the top of stack currently has 3. So from 3 we try to go to any unvisited neighbor. So we have 5 and 7 that are yet to be visited. So we pick 5. So we push vertex 5 to the stack. So vertex 5 is the fifth vertex to be pushed to the stack. So far we pushed 4 vertices. So continue the push order numbers. So vertex 5 is the fifth vertex to be pushed to the stack. And so now from vertex 5, so call that edge between 3 and 5 also as a tree edge. Now the top of stack has vertex 5, so go to one unvisited neighbor, which could be either 6 or 7. We pick 6, the lower ID, so push vertex 6 to the stack. So 6 is now the sixth vertex to be pushed to the stack. Call that edge as a tree edge. And from 6 we go further down if possible. We can go to 7, that is not yet visited. So 7 is the seventh vertex to be pushed to the stack. Now call that edge between 6 and 7 as a tree edge, because we use that visit 7 for the first time. So now from 7 we try to go further down to an unvisited vertex, but we cannot go to a new vertex because this edge to 5, now 5 is already visited. Then there's an edge to 3 and 3 is already visited. So we should simply call those edges to 5 and 3 from 7, or between 7 and 5, 7 and 3 as a back edge, because those vertices already pushed to a stack. So we cannot go further down to a new vertex from vertex 7. So it's time to pop out vertex 7 from the stack. So vertex 7 is the second vertex to be popped out of the stack. So we mark the pop number. So once we pop out vertex 7, the top of the stack has 6 in it. Now all the neighbors of 6 already visited, so we cannot go further down to a new neighbor of 6. That means it's also time to pop out 6 from the stack. So vertex 6 is the third vertex to be popped out of the stack. That means now the top of stack will be vertex 5. Now again from vertex 5 we cannot go anywhere else, so we pop out 5 from the stack. So that's the fourth vertex to be popped out of the stack. So the top of the stack will have vertex 3. And again from vertex 3 we cannot go further down to a new vertex. All the neighbors of 3 are now already classified, or visited, so, and the edges are classified. So we pop out 3 from the stack, and that's the fifth vertex to be popped out of the stack. So the top of the stack has vertex 2. So again we cannot go anywhere else from vertex 2. So we pop out vertex 2, that's the sixth vertex to be popped out. The top of the stack now has 1. Now from 1 we have 2 unvisited neighbors. You can either go to 8 or 11. So you have to be careful. We cannot just keep popping out. You have to see if you can visit a new vertex. So in the case of vertex 1, that is currently in the top of the stack, and that's also only the only vertex in the stack for now. We can go to one of its unvisited neighbors, which are either 8 or 11. So we break the tie by going to 8. So that means 8 is pushed to the stack. So 1 is still in the stack. We push now 8 to the stack. So we have so far pushed 7 vertices in the stack. So continue the push number. So 8 is the 8th vertex to be pushed to the stack. So that edge between 1 and 8 is called a tree edge. And so the top of the stack currently has 8. So visit one of the neighbors of 8, which could be either 9 or 10. So we visit 9. So 9 is the 9th vertex to be pushed to the stack, and call that edge as a tree edge between 8 and 9. So from 9 we can visit 11. That's a vertex not yet visited. So push 11 to the stack. So far we pushed 9 vertices. So 11 is the 10th vertex to be pushed to the stack. So this edge is now a tree edge. So the top of stack currently has 11. Now from 11 we can go to 10, because we have not yet visited 10. So 10 is now the 11th vertex to be pushed to the stack, and that edge is a tree edge. Now the top of stack is 10. Now from 10 we cannot go anywhere else, because we went through this order 8, 9, 11, 10. So the edge that you have from between 10 and 8 is a back edge, because 8 has already been pushed to the stack. So we label that edge as a back edge. and we cannot go anywhere else from 10, so it's time to pop out 10 from the stack. So far we popped out 6 vertices from the stack, so continue the pop number. So 10 is the 7th vertex to be popped out of the stack. So now the top of stack has 11. Now we cannot go anywhere else from 11. We have to just call that edge as a back edge to 1, because 1 is still in the stack. So this edge between 11 and 1 is a back edge, and then pop out 11. So 11 is the 8th vertex to be popped out of the stack. So the top of stack currently has 9. Now we cannot go anywhere else from 9, so pop 9 from the stack. So 9 is the 9th vertex to be popped out of stack. The top of stack has then 8, and then again we cannot go anywhere else from 8, so pop out 8. So that's the 10th vertex to be popped out. So the top of stack currently has 1. Now there's no other neighbor for 1 to be visited. All the edges also are classified, so we pop out 1 from the stack. So 1 is the 11th vertex to be popped out of the stack. So you started depth first search from 1, and you're able to visit all the vertices. So all the vertices are in one component, and also if you put together the tree edges, we can get what is called a depth first search tree. Now one thing you have to realize with depth first search tree is it cannot be used to identify or determine the shortest path from the starting vertex 1 to the other vertices. For example, if you look at the case of 11, if you go through the tree edges, the length of the path from 1 to 11 is 3, because you have 3 tree edges to traverse. So it is the length is 3 on the path of the tree edges, whereas you see there's an edge between 1 and 11, so we can directly go from 1 to 11 using this edge. So the result of depth first search by putting together the tree edges cannot be used to as the shortest path from the starting vertex to every other vertex, whereas the result of breadth first search could be used to identify the shortest path. So if you start from 1, if you go through the tree edges, so 1, 2, 4, 6, so this is the shortest path from 1 to 6 of 3 edges. That's the shortest path length. Similarly, between 1 and 8, so 1 to 8, so the path length is 2, and also the level numbers actually indicate the path length. So the starting path level number is 0. That means from 1 to itself the distance is 0, the path length is 0. Whereas to 6 the path length is 3, because that's the level number for 6 related to 1. So it started from 1 with level number of 0, and level number of 6 is 3. So that indicates the shortest path length. So that is one other thing, as I said, that you can do with breadth first search, but you cannot do the same thing with depth first search, because we go as deep as possible from one vertex to other vertex. So we are not really targeting shortest path. Whereas in the case of breadth first search, we go breadth-wise, in the sense that if you go back to this example, you started with vertex 1 with a level number of 0, and you're visiting all the neighbors of vertex 1 at the same time, simultaneously. So all the neighbors of vertex 1 are said to be at level 1. Whereas if you compare this with depth first search that we just did, what we do, we just visit one of the neighbors, and then go further down, and then go further down as much as possible. Only if you reach like a dead end, we backtrack and explore a vertex that is earlier in the stack. We don't do this in the breadth first search. What we do, we just go breadth-wise. So we push all the 3 vertices 2, 3, 7 to the stack, and then what we do, from each of those vertices you visit the vertices at level 2. So from 2 you visit 8. So now 8 is said to be at level 2. Then from 3 you visit vertex 5, it's also at level 2. Then if it's possible to go anywhere from 7, we could have done that, but in this graph we could not do that. So basically what we do now, after we push the vertices at level 1, we are identifying the vertices at level 2, which are 5 and 8, and we push them to the queue, and then not push, add them to the queue. And after we do that, we identify the vertices at level 3. So we always identify the vertices in the increasing order of the level numbers. So that's the property of breadth first search. You start with vertex at level 0, you identify vertices at level 1, then identify the vertices at level 2, then identify the vertices at level 3 and so on. So because you identify the vertices in the increasing order of the level numbers, that is what is the shortest path length between from the starting vertex to every other vertex. Whereas the same thing cannot be said with depth first search. So even though in this example, say 11 is directly connected to 1, we are not exploring that as right away. We are going through like 8 and then to 9 and then we go through 11. So the objective of depth first search is not to identify shortest path. It's just to go as deep as possible and explore the vertices and then backtrack and explore the other vertices and so on. Okay, so that is something you have to know as a difference between breadth first search and depth first search. So breadth first search can be used to identify shortest path from the starting vertex to every other vertex, whereas depth first search cannot be used for that purpose. Right, so we will stop for a minute with this and let me save this video. If you have any questions, you can ask.